in that context, I can bring one important phrase in. There's something which is called the frozen core approximation. Frozen core approximation means that has something to do with these excited determinants. And the frozen core approximation means that some of the occupied orbitals we are not allowed to touch. Because if you take water, then the occupied orbitals in the Hartree-Fock determinant, there will be one orbital, which if you look at it, essentially is nothing else than the 1s orbital of oxygen. And sort of all the story about valence electrons and the chemistry happens in the valence electron, you actually can see that. Because if you look at the molecular orbital coefficients for the lowest orbital in water, you will see that they are actually only the S functions of the oxygen contribute to that. So this is just a 1s orbital of oxygen, although it's in water. It's still the 1s of oxygen. Those are called the core orbitals. So in carbon, nitrogen, oxygen, fluorine, it would be the 1s. If you go in one row down, it would be 1s plus the 2s and the 2p. If you come to the transition metals, you can have a long discussion what is core and what is not core. And some people talk about large and small core. Anyway, but up in the organic chemistry part, that's easy. It's all the inner ones. Now a frozen core approximation is then when you make those excited determinants here, you don't replace the core orbitals. So replace only the other orbitals, the valence orbitals. And the valence orbitals, those are really mixed bonding orbitals. In water, it would be an orbital which has the 1s of hydrogen and the 2p of oxygen atomic orbitals involved. But so frozen cores, you keep typically the 1s orbitals of carbon, nitrogen occupied always in those determinants. Those are not replaced. That has an important consequence, because if this is sort of not all but 1s orbitals, then there are less orbitals which you can replace, and therefore the number of single excited, double excited, triple excited determinants which you can make is smaller, because you reduce the number of electrons for which you can use different orbitals. So you get less single, double, triple excited determinants, and therefore there are less coefficients which you have determined. The whole problem becomes smaller. The calculation becomes faster. And you're going to play with that next week first, but we're going to play with that. It's a good approximation, but you have to be careful because you have to be aware of the fact that you're using that. Because if you don't take the core electrons in here, if you don't correlate what we call correlate the core electrons, your energy is going to be different. You get a different energy whether you use that or not. But the energy differences are fine. They are almost not changed. But only, of course, if you use that for all the systems you're looking at. So if half of your calculation is frozen core and the other half not, it's all crap.